Okay, how you guys been? Long time no see in person, right? Okay, so yeah, I had to move class to virtual because I had some things going on. So, but thankfully we're back to in person. Okay, we're planning on having an exam. Let's see, when did I say that? I need to check that out. Actually, I should be on this Canvas email. Said when did I? Let's see here, it's, the messages that I sent. Let's see here. If I can't find it quickly, I'm going to move on, but I should be able to find it quickly. Here we go. Yes, next Thursday, so the 25th, we'll have our exam over chapter 2. Have you guys been studying on your own? Okay, good. That's what I expected. So what I'm going to do is we're going to go over section 26 today. And over the weekend, I'll upload the rest of chapter 2 digitally. And then Monday and Wednesday, we'll just review. You could just ask any questions you have. We'll go over example problems and stuff like that. And then we'll take the test on Thursday. All right. That way we'll have 2 review days so I can help do problems for you guys and fix any issues you guys might have. Oh, and feel free to ask any of those questions you have right now. Before I go through this, we can do a homework problem example if you're wondering on anything. Yeah, I think we're missing 1 student, 2 students. The online student is there. That's good. How's it going? So if you guys have any questions, let me know. If not, I'm about to start on 2.6. Okay. This is implicit differentiation. Okay. So the general equation for a circle centered at the origin of radius 1. This is given by x squared plus y squared is equal to 1. Now, notice what happens when we try to look at a tangent line. We can look at a tangent line, so it does have tangent lines at various points, as you can see here. So there's no problem with that. But notice that, does it obey or disobey the vertical line test? It disobeys it, so it's not a function, right? That is not a function. But what if we want to still take the derivative of this function? Even though it's not a function, we could still do it. This is the process of implicit differentiation. Notice that we can take d dx of both sides of this equation. The derivative of a constant is 0. The constant can be any number. The derivative of a number is 0. So whenever the differential operator is acting on just a pure number like 1, 2, -5, -13, it just becomes 0. Now, what about here? The derivative travels to both pieces. All right. Then it operates on here and it uses the power rule. So it brings down the power and it subtracts 1 from the power above. So it becomes a 1. So we just leave it. So 1 minus 2 is 1. So there's a secret 1 in that power. Same thing for here. Except now we have to now have a dy dx because of the chain rule. You guys familiar with the chain rule? The chain rule. We use the chain rule because y is a function of x, but x is not a function of y. X is just a variable, but y is a function of x. So we have to take a dy dx. So every time you see a y, do the normal differentiation operation and then put a dy dx. And we can denote shorthand dy dx with a y prime. Okay. And then we'll solve for y prime. So we get 2y, y prime is equal to negative 2x. Divide both sides, I get y prime is equal to negative 2x over 2y. Cancel out the 2's. This implies y prime is equal to negative x over y. Notice that y prime is a function of two variables now. It's a function of x and y. So what if we want to know, because derivatives correlate to slopes of tangent lines. The derivative of a function, whenever we input that value, it computes what is the slope of the tangent line at that value. You guys have had trig before, so you know that on the unit circle, there corresponds some point here where it has root 2 over 2, negative root 2 over 2 values, right? Right? Remember that from trig? Yep. There's a point here. So what if we want to know what is the slope of the tangent line at that point? We have the equation for a unit circle. We took its implicit derivative, and it's here. So we can just plug in the x and the y values into our derivative equation and figure out what is the slope of the tangent line at this point. Isn't that cool? So x is root 2 over 2. Y is root 2 over 2 with a negative on it. And we just plug it in there. This negative is from here. This negative is from the fact that it's a negative root 2 over 2. So they cancel. Anything divided by itself is 1 except 0, right? Anything divided by itself is 1 except for 0. So the slope of this tangent line at this point is going to be 1. That's what the slope is. Recall, a line has the equation y is equal to mx plus b. We just discovered what m is. M is equal to 1. We discovered what m is. M is equal to 1. We have not discovered what b is, but we could, right? We could discover what b is if we wanted to, because we have a point on the function. This is a point. And we have a slope. We can use point slope form to find the equation of that. Point slope form says y minus y1 is equal to m times x minus x1. It's called point slope because you have a point, x1, y1, and a slope. And with that, you can generate the equation of a line. So y minus our y1, which is a negative root 2 over 2, is equal to m, which is 1, times the quantity x minus root 2 over 2, which is our x1. So we get y plus root 2 over 2 is equal to x minus root 2 over 2. So then I can solve for y. I get y is equal to x minus root 2 over 2 minus another root 2 over 2. So this becomes x minus 2 root 2 over 2. So this becomes x minus root 2. This is our equation for our line. So that means the y-intercept is going to be over here at minus root 2. Do you guys see how I got minus 2 root 2? Something like x minus x is minus 2x. Consider this is just an x. 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 If I have negative x minus an x, you easily say that's a 2x. So if we have a negative root 2 over 2 minus a root 2 over 2, we easily say it's a 2. A negative 2 root 2 over 2. 2's cancel. All right. Now that we've discovered that, that is this line, this yellow line. We discovered the equation of this yellow line. Now let's talk about why x squared plus y squared is equal to 1 generates a non-function. notice that this right here, when we solve for y, we can get this. We take the square root of both sides. So we get y is equal to plus or minus. That is y, plus or minus. So notice that when you take plus, you get this upper half of the circle. When we take minus, we get this lower half of the circle. Yeah, so plus or minus creates the whole circle. But that's why it's not a function, because it can be both. Therefore, you have both, and it would disobey the vertical line test. Implicit differentiation allows you to get past that fact. So notice right here, we found the slope of the tangent at this point right here in the fourth quadrant. If we took y is equal to negative this, a y of x, which is a function of x, we could have actually found the derivative without utilizing implicit differentiation. Just take our normal ddx of both sides. Y prime, which don't forget y prime is ddx of y, is equal to ddx of the square root of 1 minus x squared. How do we deal with this guy? Well, we know that this is the same thing as ddx. ddx is just, it looks like a fraction, but really it's a command. It's saying take the derivative of this. I'm going to put parentheses because I can raise this to the 1/2 power. Just take what's inside the radical, raise it to the 1/2 power. It's the same thing as taking the square root of that thing. And now we can take the power rule. When we take derivatives, we have to use the power rule here. The power rule says bring the power down when we're going to take the derivative. It says bring the power down out in front, rewrite what you had, raise its power to what it was minus 1. What it was 1/2. Minus 1 gives us a negative 1/2. When you take a full 1 from a half, you get a negative 1/2. So now this power is going to become negative 1/2. Are we done? No. What do you got to do now?
I want to say the thing inside, but maybe not.
Yes, you have to take the derivative now, ddx of what's inside. Purely what's inside here. No powers, nothing. Just what was inside there. No powers involved, nothing. Just purely what's inside there. Because it's a composition of functions, you have to use the chain rule. So this was the power rule, and now we've activated the chain rule. You know to use the chain rule when you have a composition of functions. We know this is a composition of functions because we can build this with two functions. We can say let f of x equal square root of x. And let's let g of x equal 1 minus x squared. Notice that f of g of x is equal to f of 1 minus x squared, but then that equals square root of 1 minus x squared. So aha, this thing is clearly a composition of two functions. So every time you have a composition of two functions, you have to do the chain rule. So first we took the derivative of this outside function, and now we're going to take the derivative of this inside function, because this is the same thing as this. So ddx of this thing, what is that? It's quite simple. It's really quite, and I say quite simple, I don't mean that to be pedantic. I mean, really, it's quite simple. The derivative command travels to both these pieces, okay? Soon I will stop doing this, but I'm gonna explicitly do this. It will be implied after a while. I won't just do this over and over again. The derivative travels to both pieces. I'll erase this information here, actually. So then we rewrite everything. The derivative of a constant is what? Yes, the derivative of any constant is 0. The derivative of x squared is what?
1.
what is it?
No, 2.
2?
2x.
2x. Here's how you do it. You bring the power down out in front, 2. You rewrite the x. You raise the power to what it was minus a 1 each time. And so 2 minus 1 is just a 1. So you can just leave it like that. So this becomes and the 1/2 and the 2 cancels. So we get a negative x times 1 minus x squared raised to the negative 1/2 power. We can take that even further and simplify it even further if we want, or we could just keep it like that. I'd be happy if you kept it like that, but I'll also be happy if you rewrote it like this. This is the same thing as negative x divided by the square root of 1 minus x squared. Notice we're doing all that to calculate what is y prime of x. Let's see if it works. If we plug in a square root of 2 over 2, will we get a 1 again, just like here? Well, y prime of root 2 over 2 is equal to negative root 2 over 2 divided by the square root of 1 minus root 2 over 2 squared. But that's equal to negative root 2 over 2 divided by the square root of 1 minus the square. The square travels to the 2, which squares it, which gives us a 2. It travels to this, and it makes it a 4. Okay. 1 minus 2/4. When you give them a common denominator, this is 4 minus 2 all over 4. So now you just get 2 over 4, which is a 1/2. So this becomes, this whole thing becomes the square root of 1/2. The square root travels to the numerator and the denominator. But the square root of 1 is just 1. And the square root of 2 is just square root of 2. So let's rewrite that as 1 over root 2. But whenever you rationalize 1 over root 2, you get root 2 all over 2. But notice now we have something divided by itself.
Whenever you do that, you only do it on the one on the bottom right. Not on, whenever you said rationalize or something like that. Whenever you multiply by the radical. Like
Yeah, you only do it to the bottom one.
Bottom right, okay.
Mm-hmm.
Okay.
So now you guys see what's going on here. Let's do a lot of practice problems. Let's do some practice problems. Because right now it might seem weird, like what are we doing? If we do it over and over again, you might get how to just, you might understand what is the pattern. So let's do like examples. So let's do implicit differentiation examples. So what about y squared is equal to 3x plus 4 quantity squared? Okay. Before we do that, that's implicit differentiation. All right. Let's do normal differentiation. So f of x is equal to x cubed minus 2x plus 1. What is f prime of x? That's d dx of all of this. The d dx travels to each of them. I'll write it explicitly just this time, but after this time, I won't do it anymore because it'll just be implied. What's the derivative of a constant? This is 0. 0. What is the derivative of 3x? Or, I mean, x cubed?
3x squared.
3x squared. What's the derivative of 2x?
2.
Why is it just 2?
Because you take the power, which is 1, you multiply it by 2, and then it's 1 minus 1 would be 0.
Anything raised to the 0th power is 1. So you just get 2 times 1 times 1, which is just 2. Yes? So that's normal derivatives. So let's do one more example of a normal derivative. What if f of x is equal to 2x cubed minus 5x? What is f prime of x? Well, f prime of x is just d dx of all this. And I won't have the d dx here and d dx here, but we'll just do it. d dx of 2x cubed is what? 6x squared. What's the d dx of 5x?
5.
Just a 5, so we put minus 5. There you go. That's it. That's normal differentiation. Now let's do implicit differentiation. It's slightly different, okay? You take the d dx of both these sides. All right. The right side that just has only x's in it is like normal differentiation. So we bring the power down, 2 times what's here, everything raised to the 2 minus 1. 2 minus 1 is 1, so this is just a 1. We'll just leave it like that. But we got to use the chain rule, d dx of the inside. Okay. So then this becomes 2 times 3x plus 4 times the d dx of this inside. When the d dx meets the 4, it's just a constant, so it's a plus 0. That goes away. When the d dx meets the 3x, the x goes away, so this is just a 3. So this reduces to 6 times the quantity 3x plus 4. Now, here's where things get different. And I'll do it with the yellow. Power rule brings the 2 down. So this becomes a 2y. But now we have to have a dy dx. Why? Well, remember when we did the derivative here, we brought the 2 down, we repeated the value, and then we did d dx of the inside. Same thing is going on here, because y is a function of x. Y is a function of x. So when we bring the 2 down, repeat the value, we also have to take the derivative of the inside. But we don't know what the derivative of the inside is, so we just leave it as dy dx. And dy dx shorthand is y prime. Shorthand, we can call this a y prime. Okay? So we just replace dy dx with a y prime. Just because it's easier to write. So we have 2y, y prime is equal to 6 times the quantity 3x plus 4. So then we solve for y prime. So then we'll go over here, we'll divide both sides by 2y, and I'll get y prime is equal to 6 times the quantity 3x plus 4 divided by a 2y. But this becomes 3 times 3x plus 4 divided by y. This is our y prime. Let's do more examples. This will make more sense the more examples we do. What is y prime equal to if we have this equation? Y plus 3 raised to the 4th power is equal to x raised to the 7th power minus 3 sine of x plus a y. Let's clear up some space. Let's clear up some space. Okay. Y prime, what is it? Well, we got to take the d dx of both sides. Okay. I'm gonna move the calculations over here. So on the left-hand side, the 4 comes down, the power 4 comes down, 4 out in front, y plus 3. This power was a 4. What happens when you subtract 4 by 1? It becomes a what? A 3. So we make this a 3. Are we done?
No.
No. What do we got to do? ddx of the inside, y plus 3. Moving on to the right-hand side of the equation. This ddx travels to each of them. So once it hits x to the 7th, what do we get? The power comes down, 7, x to the 1 minus the power, which is a 6.
Okay.
Do we do ddx of the inside?
That's what we're doing, right?
No, I mean, we can do ddx of the inside, but the ddx of the inside is just x, and ddx of x is just 1. So it's like you're doing extra work you don't have to. So we just leave it like that. Now we move on to 3 sine of x. Derivatives ignore constants out in front. So let's do ddx of just 3 sine of x separately. That derivative is going to ignore that 3. It just wants to attack things that has x's in it. It ignores constants. It just wants the x. So then we say, what is the derivative of sine? Let's see if you guys have been studying on your own. What is the derivative of sine?
Cosine?
Yeah, like in the book, right? Did you see how it derives it using the sum of angles formula? The derivative of sine is cosine of x. ddx of the inside? The ddx of the inside of cosine of x is just x. ddx of x is 1. You don't even have to worry about it. So we could just leave this as 3 cosine of x. Now, what is ddx of y?
Seriously, 1? No. 1.
1. That's it?
No.
No, we're doing implicit differentiation. So we have to do the chain rule on y, because y is a function of x. When we say y, we mean there's x's in there. Y is like a function of x. So we take the derivative of y, the y goes away, but we have to use the chain rule. We have to say dy dx, or we could just denote that as a y prime. So what if you had something like this? Here's just a separate example. I'll put it in a box because it's not part of what we're doing. But what if you had ddx of 4y cubed? What would you get there?
12y squared?
Is that it?
No.
That part is right. You do get a 12y squared. But then what?
You need to get the ddx of the y.
Which
The
ddx of...
dy over dx.
Yeah, and so that's just a y prime. That's it. What about ddx of negative 5y squared? What does this become?
Negative 10y, then y prime.
Yeah, let's do one more for good measure. These are just example side problems. What is the ddx of y to the 10th power?
9.
9?
9y.
Oh, you mean 10y to the 9?
Yeah, to the 9.
Yes.
Yeah.
It's okay, it happens.
And then y prime.
Y prime. Does that make sense? Harrison, does that make sense?
I'm starting to get it.
Okay. With y's, it's like with normal x's. So what if we just had ddx? Let's do another box. What if we just had ddx of x to the 10? How would it be different?
Oh,
Well,
you don't have the
it just
right?
becomes 10 x to the 9, and you're done. But with the y's, because they're functions of x, you do the 10 y to the 9th y prime. That has to come. So when there's y's involved, there's just that extra step of adding that times y prime. So now, let's apply our knowledge to our problem we were doing before, this one right here. So this becomes a 4 times y plus 3 cubed. ddx of this whole thing, when ddx meets up with 3, what happens to it?
Yeah.
It goes away to 0. What about when ddx meets up with y? Yeah, it becomes a 1 times what?
The y prime.
Yes. So we could just write it as just a y prime. But you know, for thoroughness, for your learning, we'll do a 1 times y prime. But that's just a y prime.
And then you rewrite the.
Yes, you rewrite the other side. Okay. And then let's make this more simplified. 4 times y plus 3 cubed y prime is equal to 7. X to the 6 minus 3. Cosine of x plus y prime. Okay. If you recall, our original task was to find what is y prime. But we have 2 y primes. We have to find 1 y prime. But we have 2 y primes. How do we get around this?
Like separate them. One on one side.
But they're already separated. We got to do the opposite of that. We got to let them hang out.
No, like bring them together.
Yes, bring them together. Like that.
But hold up, before you do that. Like, so you know how. No, I think it's fine. I don't know. No, you're right.
Okay?
Yeah.
All right.
I think.
If you still have the question, let me know. Feel free to stop me at any time. Okay? I want you guys to learn really badly. I want you guys to learn.
Okay, I just got confused because you see how it's a 7x to the 6th power minus 3 cosine x plus 1 and then the y prime. Is the y prime like only multiplying that one or is it multiplying the whole thing?
It's just multiplying times the 1.
Oh, okay.
Yeah.
All right. I just got confused.
Yes. It's just multiplying times the 1.
No.
That's why when we rewrite it, we don't have that 1 there anymore. It's just implied that it's there.
Okay.
What about like the number 15? We don't write 15 times 1 divided by 1. But even though it's there, every number is always multiplied times 1 and divided by 1 at all times, technically, right? One could argue, and this is philosophical here, that you need 1 to exist for everything else to exist. Because 1 is like the scaffolding for all the other numbers. Now that's just like out there philosophical talk. But yeah. Now we can actually find y prime because we can factor it out. The 2 y primes will become 1. Y prime, factor it out, we get this. I factored it out. Because when I send the y prime back in, now y prime is times this and you get that, y prime times that and you get that. I think I have some chalk in my eye.
So hold up. So you keep going. So what did you do on that part? Like with the y prime?
I pulled out a y prime out of each of these terms. When you pull out a y prime out of here, you get a -1. When you pull out a y prime out of here, you just get this stuff without the y prime.
Oh, okay.
So now I can divide both sides by this piece right here, and we could solve for y prime. Because our goal was to find what was y prime. Remember?
Yeah.
Woo! Woo! Good thing it didn't land on my head. Did you you guys see that dodge?
Yeah.
Had to dodge the eraser. If it landed on my head and I just walked out on the street, people would think I'm like weird, you know? It's like, what's that in his hair? They won't know I'm a teacher. They'll think it's like something else. Okay, we'll move this over here. This is a y prime, don't forget. Divide both sides by what's inside here, this bracket here. And then you get y prime is equal to what's over here. 7x to the 6th minus 3 cosine of x. Divided by what was in there, 4 times y plus 3 cubed minus 1. And you're done. That's what y prime is. So you guys need to get good at doing implicit differentiation. It will definitely be on the exam. Implicit differentiation will definitely be on the exam. You'll have a situation just like this, and you'll have to reproduce this stuff.
So is that the end of it?
This is the end of it. Yeah, I usually box it, don't I? Yeah.
Of course, if you can like simplify, like you would simplify, right? And then that would be the end.
Yeah. Yeah. This is as simplified as it gets. Yeah.
Because you could do you think you can do one where you do the derivative like where you have like a division, you know what I mean? Like a fraction.
Yes. 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 That's a great request. That's a great request. For sure. Because you want to review the quotient rule, huh?
Yeah.
There's the product rule, then the quotient rule. We haven't talked about this in class because class has not been in session. I've been uploading videos, but I upload those videos and I have no idea if it's getting through to you or not, you know?
I watched that video and like the product rule, I think it's really easy. And I mean the quotient, it's not hard, it's just like there's more steps to it. So,
Yes, that's right. That's right. Product rule has to do with what is the ddx of two functions times each other. The quotient rule is what is the ddx of two functions divided by each other. The product rule states that this becomes f prime of x g plus g prime of x f. One of them gets differentiated while the other one stays fixed. Then you add it to the other one that gets differentiated. Now the opposite one gets fixed. When I write f prime of x, that means ddx of f of x. When I write g prime of x, I mean ddx of g of x. The quotient rule is like so. You take the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. Why is that so? It's in your book. I can show it to you, but for the sake of time, I'm not. But there's a reason for why the derivative of a ratio of two functions is this weird formula versus this straightforward formula. It can be shown. You actually don't need the quotient rule. You can just do the product rule by saying that this is the same thing as this. That's my hint on how you derive it. You could say, oh, that's just g to the negative 1 power, and then just use product rule. And then it will derive this right here. So let's do an example of the quotient rule. What if y of x is equal to, let's do something just very simple, x cubed divided by x squared minus 1. What is y prime of x? Well, that's the ddx of this. And the ddx of that invokes the quotient rule. So I'll erase the product rule here. That uses the quotient rule. So that's equal to the bottom function times the derivative of the top minus the top times the derivative of the bottom. Everything divided by the bottom squared. So then we just go about our business. This thing just stays this thing. It just goes along for the ride. What has the prime on it gets differentiated. You bring the 3 out front and decrease the power by 1. Then you move on. This just becomes x cubed, but we're differentiating this thing, this whole thing in the parentheses. That's why it's got a parentheses and the prime is around the parentheses. When it hits this, it just becomes a 0. Go away. When it hits this, it becomes a 2x. And that's that. And we divide it by this thing. No derivatives, nothing. It's just that thing squared. And you're done. You're done. That's it. Now, don't forget, you may have to use the quotient rule in conjunction with the chain rule. You may have to use the quotient rule in conjunction with the product rule. Actually, yeah. Let's do an example of that. One where you have to do the chain rule and the quotient rule. What if your function f of x is equal to square root of x minus 1 divided by x squared? What is f prime of x? Well, f prime of x is equal to dx of this guy. But by the quotient rule, that's the bottom times the derivative of the top minus the top times the derivative of the bottom. Everything divided by the bottom squared. So this becomes, don't forget that the square root of x or the square root of x minus 1 is the same thing. I'm just going to rewrite everything like so. And I'll just replace the square root and I raise the whole thing to the 1/2. Now let's take the derivative. This becomes x squared times the derivative of this thing is 1/2 out in front times the thing raised to the 1/2 minus a 1, which becomes a minus 1/2. And then you have to do d dx of the inside, which is just a 1. The d dx of the inside, that just ends up becoming a 1 because the derivative of that minus 1 is a 0. The derivative of x is just 1. But notice we're using the chain rule. Minus, and the derivative of x squared is 2x. Everything over x to the 4th. And you're technically done. You just got to simplify it a little bit, clean it up a little bit. So this becomes x squared. This becomes the 1. So this is, you can say goodbye to it. This becomes x squared divided by 2 times x minus 1 square rooted minus 2x square root of x minus 1, everything over x to the 4th. Or you could have just kept it the way it was. Or you could have just said, oh yeah, that's just the same thing as x. That's the same thing as 1/2 x squared x minus 1 raised to the negative 1/2 minus a 2x x minus 1 raised to the 1/2. Everything divided by x to the 4th. Either of these work. Now, let's do one that's going to involve the quotient rule and implicit differentiation. This is going to take a lot of board space. What is y prime if we have 2x minus 3 divided by 7y to the 4th plus 5x is equal to sine of y? What do we have here? Well, y prime is equal to the d dx of both sides of this. To find y prime, we have to do that. That's not y prime equals. To find y prime, we have to take the derivative of both sides of the function. Derivative of this side, derivative of this side, and we're supposed to find what y prime is. That's why we take the derivative to discover what y prime is. So over here, the derivative of sine is what? Cosine of y. And are we done?
No.
Y prime. Because the derivative of the inside function is dy dx. And dy dx is y prime. Now we got to use the quotient rule here. So this is equal to the bottom 7y to the 4th plus 5x bottom times the derivative of the top minus the top times the derivative of the bottom. All over the bottom squared. And I'll put this cosine of y over here. Cosine of y prime. Right here. So then we move our calculation over here. Cosine of y prime is equal to, this thing just comes along for the ride. 7y to the 4th plus 5x. We just don't touch it. It just comes along for the ride. We take the derivative of this thing. Derivative of 3 is 0. Derivative of 2x is just 2. This thing now comes along for the ride. And now we got to take the derivative of this guy. What's the derivative of 7y to the 4th?
Y 3 and then y prime, right?
Yeah.
And then plus 5.
Yeah, precisely. Divided by this whole thing squared. Now, we got to solve for y prime. There's a y prime here, There's a y prime here. We have to make them hang out so we can factor it out. And that's going to require some work. So this is going to equal 2 times this whole thing. We can just keep it like that. But now we have to FOIL these two. Okay? So minus, let's FOIL. 2x times 28y cubed y prime becomes what? What happens when you double 28?
When you double it,
Yeah.
It's
56x y cubed y prime. And then the 2x times the 5 is plus 10x. Now, when 3 times 28, what's negative 3 times 28? Negative 84 y cubed y prime. And what's that minus 3 times the 5? Yeah. And now we have to distribute that minus to each term, this right here. We can call this a plus if we distribute the minus to each term. Distribute that minus to each term. That's why it's important to put these brackets out when you FOIL, because this minus sign was out here. Now that we let this minus sign go through all the terms. Now, what? This term doesn't have any y primes, so we just keep it the way it is. This term has y primes, so we're trying to meet up with the y prime over here on the left-hand side of the equation. Okay. This is equal to cosine of y prime. So we multiply both sides by this. So we get cosine of y prime times 7y to the 4th plus 5x, everything squared, is equal to this. Okay. Then what we want to do is we want to make the terms that have the y primes, like this guy, and this guy, hang out. So we'll send those terms on the right side over to the left-hand side of the equation. So this is plus 56 x y cubed y prime minus 84 y cubed y prime. That's going to equal 2 times the quantity 7y to the 4th plus 5x minus the 10x plus a 15. So then we can send this 2 actually into here, making this a 14y cubed plus
before you do
10x.
Yeah. Because you, no, I was looking at the other one. Right.
Say what?
No, it's because I thought it was the one up because you missed the square of the 7x squared, but on the one on the top.
Yeah, it's up there. Yeah, so you distribute the 2, then you can cancel out the 10x's. Okay. And then once you do that, the 10x's go away. So this becomes plus 15. And you can rewatch the videos, so that's why I'm doing this stuff. And then you factor out the y prime out of the numerator. And you're almost done when you do that. That's the penultimate step. So out of the top, we factor out a y prime. So you get cosine of y times this 7y to the 4th plus 5x plus 56.
That's squared. That one's squared.
There's a square here?
Yeah.
Okay. Plus 56xy cubed y, the y prime goes away, minus 84y cubed. That's equal to 14y 4th plus 15. And then we divide both sides by what's here in this bracket, and we're done. Easy as that. It's just a lot of algebra. There's just a lot of steps.
Yeah.
Say what?
It's a bunch of stuff.
It's a bunch of steps, yeah. But in theory, it's not that difficult.
It's not hard. You just sometimes get like a little bit lost or like.
Yes.
Because it's long.
You have to stay focused. If you zone out, you're gonna make a mistake. So if your brain is feeling fried, take a break, take a deep breath, kind of relax, and then try it again. And that's that. Class has been over for 7 minutes. You guys